Hi, and welcome to the world of instrumentation and control. Today we are going to talk about RTDs. The letters RTD is an acronym for Resistance Temperature Detector. It is a type of temperature measuring sensor that operates on the principle that metal wires change their resistance in response to changes in their temperature. What that means is, by measuring the resistance of that wire, you can determine the temperature of that wire. Now, you may hear or read other names. I myself prefer resistance temperature device, and some people use the simpler resistance thermometer. But whichever term you want to use, they all mean the same thing. The wire in RTDs can be made from several types of metals, but the most commonly used metal is platinum. Platinum RTDs are quite expensive, but the advantages outweigh the disadvantages. Platinum RTDs are corrosion resistant, has an acceptable nonlinearity, has very good long-term stability, very good accuracy, and can be manufactured to have a temperature range of minus 200 to 850 degrees centigrade. There are three ways of manufacturing RTDs: thin film, wire wound, and coil formed. Thin film RTDs are made by depositing a thin film or layer of metal onto a ceramic substrate. The metal layers then etch to form a pattern that can be trimmed to create the resistance characteristics of the RTD. This pattern includes a pair of solder pads upon which wires are soldered onto and covered with a dollop of glass or ceramic. Finally, a thin coating of glass is applied to the whole thing for overall protection and robustness. Thin film RTDs have very good vibration resistance and is easy to manufacture. This makes it the cheapest construction method. Their accuracy, however, is the lowest among all the construction methods. Wire wound RTDs start out with a glass or ceramic core around which the RTD metal wire is wound. After connecting wires are attached to the RTD, the whole thing is encased in glass or ceramic. Wire wound RTDs are vulnerable to shock and vibration, but have better accuracy and stability than thin film RTDs. The glass encased type can be immersed in water, but is limited to temperatures below 400 degrees centigrade. The ceramic encased type can be used from minus 200 up to 650 degrees centigrade or up to 850 degrees centigrade with special construction, albeit with reduced accuracy. The coil type RTD uses a ceramic cylinder with holes drilled into them. The RTD metal wire is formed into coils and inserted into these holes, which are then loosely filled with fine ceramic powder to stabilize the coils. The whole thing is then encased in a ceramic coating. A variation of the coil type RTD uses a support structure with the platinum coil loosely wrapped around it. It is encased in a sealed housing filled with an inert gas. This type provides the very best accuracy among all construction types, but is very delicate. For this reason, it is never used in industrial applications and is almost solely used by calibration laboratories. Both wire wound and coil type RTDs are difficult to manufacture, and this makes them more expensive than thin film type RTDs. The advantage of wire wound or coil type RTDs over thin film types is that they are, generally speaking, more accurate. The substrates of the thin film RTDs tend to expand and contract with changes in temperature, and since the RTD traces are bonded to the substrate, the resistance change in the RTD is due to the change in temperature and the change due to the expansion and contraction of the substrates. RTDs are rarely used as a bare sensor. They are usually inserted into stainless steel probes to give them protection against the process or materials they are measuring. This slows down their response quite significantly. However, probes with tapered ends and tapered stems offer improved performance due to the thinner walls where the RTD sensor is located. RTDs have a nomenclature that helps us identify what type they are. A typical nomenclature looks something like this. The letters are the chemical symbol for the type of metal used in the RTD. In this case, the letters PT is the chemical symbol for platinum. If this were a copper RTD, the letters would be Cu. If this were a nickel RTD, it would be Ni. The 100 stands for 100 ohms. This is called the nominal reference or base resistance of the RTD. Nominal resistance is the resistance of the RTD at a specified temperature. The specified temperature, also known as the base temperature, is usually 0 ohms degrees centigrade. What that means is this PT100 RTD has a nominal resistance of 100 ohms at 0 degrees centigrade. Note that not all nominal resistances have a base temperature of 0 degrees centigrade. Copper RTDs, which has a nominal resistance of 10 ohms, has a base temperature of 25 degrees centigrade. It's actually possible to purchase an RTD with your desired nominal resistance and base temperature, but this will be a special order and may be expensive. The 385 in the nomenclature is a shortcut for 0.003851 ohms per ohm degree centigrade. This seemingly complex number is the RTD's temperature coefficient. The temperature coefficient of an RTD is the average change in resistance per degree change in temperature over a range of 0 to 100 degrees centigrade divided by the resistance of the RTD at 0 degrees centigrade. Now, there are several values of temperature coefficients for RTDs. There is 427, which is used for copper RTDs, and there's 672, which is used for nickel RTDs. In the case of platinum RTDs, there are several. There's 3902, 3916, 3926, and the previously mentioned 385. The temperature coefficient of RTDs is a little difficult to understand. I'll be making a separate video for that so that we can focus on the explanation of its concept and use. Okay, now we're going to talk about the accuracy of RTDs. Platinum RTDs are the most commonly used RTDs in the industry. For this reason, we will focus on platinum RTDs on the topic of accuracy. There were originally 3 accuracy classes for platinum RTDs: Class A, Class B, and Class C. Class A being the most accurate and Class C being the least accurate. It wasn't long, however, that the industry came up with 2 more classes, DIN 1/3B and DIN 1/10B. For some reason, both DIN 1/3B and DIN 1/10B have been renamed. DIN 1/3B is now known as Class AA, and DIN 1/10B is now known as Class AAA. If you ask me, it's easier to say Class AA or AAA than DIN 1/3B or DIN 1/10B, so this makes sense to me. Now, just a little bit of trivia. DIN 1/3B has 1/3 the accuracy figures of Class B RTDs. That's why it's called 1/3B. In the same vein, DIN 1/10B has 1/10 the accuracy figures of Class B RTDs, which is why it's called 1/10B. If the accuracy figures seem a little too complicated, this chart might help. This shows several things about RTDs. First, the magnitude of the errors for RTDs is smallest at 0 degrees centigrade. Second, the magnitude of the error gets larger the farther away from 0 degrees centigrade your measurement is. Third, the higher accuracy classes have a shorter temperature range than the lower accuracy classes. This does not mean that the higher accuracy classes cannot be used at temperatures beyond their range. It just means that the accuracy figures apply only within their accuracy range. If you measure temperatures outside of that range, the accuracy is no longer guaranteed. In fact, the accuracy of Class A, AA, or AAA RTDs revert to Class B if you use the higher class RTDs beyond their recommended temperature range. And that's it for this episode of the World of Instrumentation and Control. In our next video, we'll talk about the different wiring configurations for RTDs. You'll learn about the characteristics of each type, the effects of length of lead wires, and how compensation for lead wire length is achieved. Thank you for watching, and I'll see you next time. Bye-bye.